Hello, good morning, everyone. I am alive. Am I? Hi. So let me show you my screen. We are going to code Wolfram Language today, geometry. So you see, this is what we're gonna code. This is called caustics. This is light rays reflected off of a circle. Reflection and refraction. So when you draw this kind of thing and the envelope of the lines forms a shape, and that is called caustic. Well, the whole study of this kind of thing is called caustics. Okay, so you can see several other examples. The most famous is parabola. Okay, and then I just have a bunch of other, arbitrary kind of interesting arbitrary images of the light ray reflection to arbitrary curves and see what we get. So there are many curves that are that turns out to have relationships being a caustic of another famous curve. For example, seesaw of diagonals, this curve. So this curve is, let's go back, is the if you put a light source on the focus of this seesaw curve. Now where's the focus? I forgot where is the focus. Anyway, then the result is a cardioid, is this one, which is rolling a circle around another. Okay, so anyway, that's the things we're gonna code. Actually, we're gonna code Wolfram language. So let's begin. So Wolfram language such that it will, wait, did we begin it? Yes. So it will be able to draw any parametric equation in the caustic, the lines of any. So let's see. So you see the caustic. So if you have a circle and you have a light source on the rim of the circle, then it will, the light source reflects off the circle and creates this S-shaped curve. That curve is called cardioid. This one, which is defined by rolling a circle around another circle. You see, is that fascinating? You see, magically, you see, you create a curve by rolling a circle around another, like a coin, if you take out 2 quarters. So this curve is called cardioid. Cardioid means heart-shaped, okay? But then if you have a circle and you have a light source on the rim of the circle and you shine a light ray, they will reflect off the circle and form so-called envelope and form the cardioid too. And you can see that often in a cup, in a coffee cup. So this is amazing mathematical properties, and there's tons of it. There's lots of more, okay, lots of more. So we did a lot of coding of curves in the past few weeks. Watch my YouTube, you'll see a lot of them. But today we're gonna just code this one. Okay, so go back. We were talking about caustics. All these images needs to be updated because they were created 30 years ago. In 1994, beginning 1993. Okay, so yeah, so we're gonna, and today specifically we're gonna start with this one. So this one right now is, here is a code. It's done by one of my packages. Okay, paste the code and magnify. Okay, fantastic, and Control-Shift-N to typeset it. You can see you get a fraction, and Shift-Enter to run it. So fantastic and beautiful. Is that beautiful? So this is light rays from above reflecting off of a circle, and it forms that shape. And I believe that shape is nephroid. Does it say? Yeah. Right, nephroid is the catacaustic of a circle with parallel rays. What does catacaustic mean? Catacaustic means the curve that's formed by reflection. Okay, so so you see this light ray coming from above, you have all these reflections, then they form a curve. The envelope of these rays forms a curve by reflection. Okay, now the other part here is refraction. Okay, but we are talking about reflection. So the curve formed by the envelope of reflection rays is called catacaustic. Meanwhile, if it's refraction, then it's called diacaustic. Okay, did I explain? Catacaustic and diacaustic. Okay, so you see this reflection, catacaustic. This refraction, yeah, you see, that's diacaustic. You see, they also kind of created over there, but you see, the images here is too small, hard to see. That's why we are writing the code today to update it. But anyway, so I already have the code, of course. You can get it by plane curve plot. Search the web, Xah Lee on GitHub, you'll find it, okay? But what we're gonna do today is to write this code independently. So you don't need the package. So along the way, it'll take an hour. I'm gonna going to show you guys how do you draw these things. So, okay. So hello, JJ. So if you are here, say hi. Love to see your comments. If you are not here, play at 1.5 speed or faster. Because I'm just gonna go slowly, have fun, you know. This coffee, honey coffee, fantastic. Wait, can we see the caustics? Let's see. This is very interesting. So we got the light. You see, it shines. So can we see the coffee cup? Can we get some kind of like caustic going on? No, that's like a moon. So you need to be like above, right? Do we see it? No, shit. Okay, not really. Okay, you need to be, I think the light needs to be much stronger. Okay. So yeah, either the light needs to be much stronger, or the you need like clear, I think clear cups will show better. Okay, so where's the photo? So let's see the photo. Wait, not here. So let's go to cardioid. Okay, let's show the photo. Go to cardioid. That's rolling a circle of another, and or reflection of light rays off a circle. So there. Okay, so yeah, you can. Okay, so you need more. So I need to drink more. So the liquid needs to be low in a cup in order to see this cardioid light effect. So I'm gonna just massively drinking it. Can we actually see it? A little bit, okay? Now can you see? Can you see like the cardioid effect? Yeah, you can see a little bit. Okay, the light needs to be stronger. But anyway, stop. Okay, So let me be right back in 10 seconds. Okay. It's getting hot. Okay, let me tell you guys, what do you need to do in order to draw this? Like, what is the mathematics involved? Okay, what is this? Stop that. Okay, so what is the math involved? So you go to so what you have to do, basically not difficult. All you want to do is you want to find the tangent. Okay, so first of all, you have a curve. You need the equation for the curve, of course. For the circle, it's cosine psi. You can just plot x squared or whatever. First of all, you need a curve. Then you need a bunch of points on the curve where you want to be able to find the light ray will hit that point. Okay, so that's a bunch of parameters. Then so for each of these parameter, for each of these point on the curve, you want to find the tangent, okay, at that point. Now, tangent, how do you get a tangent? Very easy. It's just the derivative of the x formula and the y formula, just a derivative, okay? So you get a tangent line. Then what you want to do is you want to reflect. You see, when you have a light source shooting down, you want it to reflect off the tangent line, so it will go into that direction. Okay, so of course the light ray, you need to draw the light ray from a given source. So in our case, it's from x equals to 0 and y is 5,000. It's like way above. So from that point, you draw a line to the point on the curve. Then you find the tangent, but don't draw the tangent. Okay. Then you find the reflection. So given a line and given another line, tangent line, you can find the reflection or the refraction. Okay, which is basically just rotating the line 90 degrees. Not 90 degrees. It's involving like swapping the coordinate and negative one of them, something like that. I'll show you. Okay, I don't remember offhand. So it's mathematics. So you just find the reflection or refraction and just draw that line, and that's it. And you do this for a bunch of points. Okay, so we got lots of examples we have already showed. Okay, so let's code it. Okay. From Wisconsin. Hello from Wisconsin. Wisconsin is the cheese town, cheese state. Am I right? Because I had a boss kind of from Wisconsin back in 1990s, back in 1991 actually, like 1991 when I was like 20 years old. She's from Wisconsin. And she's got Wisconsin accent. I can still remember. Make a copy. Can you make a copy of this paper? Not copy, but make a copy. Is that right? Is that Wisconsin accent? So anyway, that was fun times, when I was 20, 30 years ago. Close to 40 years ago. Anyway, so so we want to start to code. Okay, Go to nephroid. We want to start to code. Let's get on to this code. Haha. Okay, so let's get on to this code. Okay, so yeah, so now remember we need the tangent. Okay, now once we got a tangent, everything is easier. We just, so first of all, so how do you get a code for tangent? Well, let's just copy. Make a copy our code from a few days ago. So let's go to evolute. We just created this code. Wait, not evolute. Let's go to envelope. We wrote this like 2 weeks ago or 3 weeks ago. Here's a code for that, but we created a independent page for tangent. This is shiny page for tangent. Let's copy that. In fact, tangent and normal, you also need the normal, because when you start to talk about reflection, we're gonna do a lot of that. You see, vector, this is about vector geometry, vectors. So copy the code. Okay, so what are we doing here? So let's go to well, let me just show you. Okay, so copy the code, paste the code here, shift enter. So you got a bunch of tangent lines and normal lines. Normal lines are defined to be the lines perpendicular to the tangent and passing the tangent point. Okay, so we got the code. So nephroid. Okay, so we wanted to redo which one? This one, semicircle. Okay, caustic of a circle or cardioid. Hot. I've been told accent. What? So not that. That's again that's interesting by itself, because the nephroid curve is okay. I should stop talking about it, because if I start to talk about it, it's gonna be non-stop. Anyway, the nephroid is a curve you can define by, there are many ways to define it, but one of the most popular way of defining the curve is a circle rolling on another circle, but the circle outside of a circle. A circle rolls on another circle on the outside of the circle, but the rolling circle is half times smaller. The radius is half times smaller, so you get that. Okay, so that's how you got this like double S shaped. Okay, that that is something else. Anyway, so the double S shaped curve. Ah shit, I need to update this page. Anyway, so that's nephroid, right? And there are so many other properties. Another way to define it is you shine a light ray, parallel lights onto a circle. Then the envelope of the reflections forms the cardioid. So that you see that is exactly nephroid. Okay, this is called nephroid. Okay, so there's lots of properties. Okay, but yeah, so what are we doing? So but we were talking about, well, what about that one? Well, that is another property. Another way to define it is you so we did this yesterday, fantastic and beautiful. Yes, we coded this yesterday, and here's a code. But we want, so this I did offline last week, something like that. So this is nephroid is the envelope of a set of circles with centers on a base circle B and tangent to a fixed chord that bisects B. So in other words, you start with a circle. Imagine here, okay? So you start with a circle and you cut in half. You draw a line passing the middle of the circle, okay? Then you draw a bunch of other circles centered on the rim of the circle B, okay? Fixed circle B, centered on the rim of the circle. But however, each of the circle you draw should touch the bisector of B. then you form this kind of thing. So the theorem is saying that you see the envelope, the formation, the envelope of this bunch of circles is a nephroid. Is just like rolling a circle. Is a nephroid. Okay, magical properties. So that's why you study the Visual Dictionary of Special Plane Curves, the project I created 30 years ago when I was young, which got me a job at Wolfram Research. That's true. I did this. That got me a job at Wolfram Research, and it turned out that's basically the most I've done for mathematics. Kind of sad. Yeah, see, really, kind of sad. Anyway, let's go back to code. Okay, so we wanted to so again, what is it we want to do? Yeah, this one. So let's focus on that one. Okay, don't get distracted. So let's copy. So let's go to does that make sense, guys? Say something. You guys watching, does that make sense? Reminds me of some X screensaver. Who making hearts? I'm only on here. Don't know who else say hi. Okay, so what is this? So caustic. So this is this is a curve we want to do, and let's create Wolfram language code. Okay, now let's start to show you. Okay, a circle. First of all, a circle is cosine sine. Okay, so let me just show you guys. Okay, a circle is x cosine sine, cosine and sine. Okay, now range least. So cosine sine. So let's see. So typically cosine sine, it starts from right, I believe. So let's say okay, so range least is gonna be a range, let's say from 0 to pi, and pi divided by 7. Okay, let's say 7 points. Okay, this just means this is just like Python range. Okay, let's run it. You see that symbolic result. Now if you want numerical result, just give a number, one of the number approximate, then it returns numerical result. You see, fantastic, supreme Wolfram language. By the way, you can download it free. Just search for my website. For example, this is website. This is my talk show, January 30th. Okay, that's interesting topic. But anyway, so go to today's talk show, download Wolfram language. Okay, just search the web, xahlee.info. Wolfram, download Wolfram engine. You can find on www.wolfram.com/developer. Turn on JavaScript, and you can download Wolfram engine, which is this Wolfram language. That's about 4 gigabytes. Okay, you need to give your email and stuff. So it's like for student, for personal use. So read their license. Okay, you have to read their license agreement and whatever. So you can download it and then just read my articles. You also want to download. So once you download the Wolfram engine, you have the Wolfram script, which you run in terminal like that. You see, you run in PowerShell or in Bash in terminal like that. But if you want the graphical user interface, then you have to download, just like read my page, download the Wolfram Research for Jupyter, Wolfram language for Jupyter. Wolfram Research created it. Now there's alternative, so there is actually someone else wrote a open source alternative to to the Jupyter. It allows you to run Wolfram Language on a website, of course, with the Wolfram engine you have to download. But, read my website, you will find it, again, so my website, Xah Lee Wolfram Language tutorial, you will find it, okay? Also, I have not been able to update my website in the past month for technical reasons, but that should be fixed in a few days. I saw the tangent line. Yes. Yes. Okay. So let's go back. So let's start to code again. So code. Okay. On Twitter, because I haven't been updating my website for technical reasons, but I have posted Wolfram Language code to Twitter. So for those of you who can't wait to grab, the Wolfram Language code, for example, this one, we coded yesterday, and the updated code is here. You don't need to download my package. Otherwise you can get the package, but if you just want to run it, so there's a code, and several others, several others I've done in the past. Anyway, on Twitter, so you just have to remember today's date, then search for it. Anyway, so we okay, we're gonna never finish at this rate, so let's start to code. Okay, range list is just a list of numbers. Okay, and let's just say n. Okay, so that makes it numerical. Okay, then okay, so tangent line length, we don't care about that really. Okay, so for now, leave it. Okay, now here is the tangent vector. So here is a derivative. So you see, f curve defines a function. It returns a list of two values. Okay, so essentially it's two functions. Okay, in a list. Now f curve prime, that is a derivative. That's a Wolfram Language syntax. So this f tangent vector is a derivative function. Okay. Then what we want to say is just to show the curve. So here we plot the curve from 0 to 2 pi. No, let's plot it from 0 to pi, just half of it. Okay. In fact, we can just copy it, and let me just show you so that you see something interesting. Okay, paste the code, Shift Enter. So you begin to see half a circle and all these tangents and normals. Okay, so go back to the code now. Plot range. Let's plot range. We don't want like that. You see, this plot range is off. This looks like the Japanese wartime flags, and so plot range is -1. Since this is like a circle, -1, then just times 1.3. Okay, copy all, select all, paste, Shift Enter. Fantastic. Now there's something, you see, we can increase the range, let's say pi over, let's say 20. Okay, then we got something else wrong. So you see the normals is going all around. The normals are not following the tangent for some reason. So you see, so this is normal line length. Okay, so let me work on that. So tangent line length, normal line length. Okay, so this is a derivative. Show this is the curve. This line plots the curve itself, which is a semicircle. Okay. Now the tangent line is the Okay, so we got Wolfram language is kind of nested, so it's all nested thing, kind of hard to read. So so x point is a point by evaluating the f curve at parameter t. Then this line normalize f tangent vector. You see, that's a derivative. So you evaluate the derivative at t, that gives you the tangent vector. Then you normalize, which is a function, which make it a unit vector. So it's a vector of length 1. Okay, so that's, we name it unit vector. Okay, now let's highlight that. Okay, unit vector. Then what we do is we let's see, unit vector times tangent line length. That because we wanted to draw, the tangent line at certain length, otherwise it's too short. So do we need that? Not really. So so this is tangent vector, this is normal vector. So what is going on here? So actually, let me do this. You see, this formatting make it more intuitive. Okay, that's what we want. Okay, so yeah, so that's kind of more. Let's make it. So this is actually one line, one thing. Okay, so this is the tangent line, tangent vector. No, this is actually tangent line. This is normal vector. Okay, that's not a line, that's a vector. Then the line, the tangent line is this, point minus tangent vector and point plus tangent vector. So that gives you the beginning point and end point of the tangent line, and color it red. Okay, so if you don't want tangent, comment out that, and we can plot it. You see, select all, paste, shift, enter. You see, we remove the tangent line. Now, so we can see why we get, so the normal, you see, we got this part because the normal lines are long. It's not because they are from the curve, you see. That's why. So our code is good. Okay, our code is good. Now, you see, because we want it not to, we want to draw the light rays. So we need light rays. So we actually need to draw light source. Okay, so light source needs to be, you have to specify a light source. For now, let's say 9 and 20, something like that. Okay, just a point. And then you need to draw a line from the light source to the curve, to a point on the curve that represent the light ray, right? So that's what we're gonna do. Okay, so you got the light source there, and you need to remember that is tangent, so copy that. So you want to draw a line from light source there to the point on the curve there. And this line, let's color it cyan, because cyan is usually like a light. Okay, and this tangent line we don't need. Okay, copy. Now select all, paste. Now Control Shift N to make it typeset. So we see this fraction is a little typeset. You see some of the brackets got larger. You see when you typeset, you see N means give numerical result. So range 0 to pi over 7. That means divided pi by 7 subdivisions. So give us 8 numbers. Then N means make them numerical, not symbolic. It can be symbolic, but slow things down. So it doesn't. So you should it doesn't matter, but if you have lots of numbers, it's much faster when you have numerical evaluation. Okay, so you see, so here's the code. So let's shift enter run it. So fantastic. Can you see the light ray, okay, from the top? Now let's make the circle from the bottom, because that makes more, because it's more intuitive for us to think of the light coming from top for this illustration. You know, we can make the light source come from any direction, but it's more intuitive they are from top. And since we want to illustrate the property of the God, where are we? Oh God, we want to, oh God, we got so many other things, beautiful things. Okay, so we wanted to illustrate. Where are we? Okay, we need to go to the nephroid page. We want to illustrate this reflection of light rays. Therefore, let's make the circle go from here to here. Okay, so let's change the range from pi to 2 pi. Fantastic. Okay, and let's make it, let's say 12 a bit. Let's say 12 a bit more. Okay, and so copy all. So let's do it again. Select all, paste, shift enter. Fantastic. Okay, this is still wrong. Okay, yeah, well, that's because here yeah, plot, you want to go from pi to pi to 2 pi. Okay, copy, select all, paste, shift enter. Fantastic. Now better. Now you see these normal lines, that's no good. You don't need these normal lines. Okay, so remove the normal lines. Okay, so remove the normals. Okay, copy all, back, select all, paste, shift enter. Fantastic. Now we just need to draw the reflection, you see. So the question, in order to do that, you need to answer this math question. The math question is given a vector. How do you find its reflection? Okay. So hi JJ, I saw the tangent line. AI sent me here because Emacs. Oh, fantastic. We got an Emacs fan, of course. I'm an Emacs master. Do you know about my Emacs tutorial? Like, have you heard of me before, JJ? Because I'm well known for that. And in fact, most of my past videos, hundreds of them, 500, like by now I have 700 videos, but I would say 500 of them is all about Emacs. So can we go to today's talk show? Let's put this back, okay? Syntax correct, show in browser. So we are working on this page, and go down. So we are working on this graphics, and this is the current code, not done yet, okay? Now this is a polished code but you require my package. You have to go get it on GitHub. Plane curve plot. Okay, but now let's go back to talk show. So show today's talk show. So you see today's episode 777, not 666, the number of the beast of the Christians thing, but 777. So I've done that many videos, but in the past, like most of it, more than half, is about Emacs. So are you still here? Like, can you right? And I mean, like, did you hear about me before, or was it first time you saw my name? Okay, cheers. So let me continue How many people are watching now? Like, not many. 3. Okay, something like 3. Okay, 5. Okay. So anyway, so does this make sense, right? So far so good. Cheers. You see, now let us take a moment to observe the beauty of code. Fantastic. I mean, imagine mathematics. You see, mathematics. Okay, Shift Control N. You see, we got mathematics, fractions, notation. You know, this human knowledge of 2,000 or 4,000 years. Exactly, that's what they are. You know, calculus, derivatives. You know, Newton, Leibniz, Archimedes. You know, Newton and Leibniz, they kind of invented calculus in 1800 or 1700, or was it? Yeah, I think 1700. But then calculus has its origins from like 2,000 years ago, Archimedes and others. And you know, so the knowledge of humanity, you know, part of it is here. It condensed into this code and computer, and not to mention the science of computation, the binary digits, you know, huge number theory. It's all here. You see, you are looking at the knowledge of human knowledge fruit, and of course, computational geometry. How do you implement this? You know, all this linear algebra and all that. Fantastic and beautiful. I have to watch. I asked about the idea of modifying stuff. I have to watch. I asked about the idea of modifying stuff. I don't know what you're saying. How old are you? Are you like pretty young? Like, I don't know what you're saying. I have to watch. You have to watch what? My videos? And you say I asked about the idea of modifying stuff. Modifying what stuff? About using Emacs to modify code, or what? Okay, so let's go back. So yeah, so how do you reflect the curve? Well, actually, I don't remember because, but I have the code. Let's just look at the code, okay? And, you know, so this we right now we face the question: given a vector, how do you find and given a vector? Let's say the vector hits like, how do you want to phrase it? I mean, the basic question is, given a vector and given a line in a plane, find out their intersection point, of course. Then, well, given two lines, okay, find the intersection point and find the other line that's the reflection and also the refraction. Let's just simplify, just say reflection. How do you do it? Okay, now in order to answer that question, first of all, you need to be precise. For example, we can start to draw. Well, so what I'm doing here is kind of education, okay, kind of like let me start a drawing program first. So I'm kind of trying to do education, tell you guys, for those young students, about how to think about mathematics, okay? So where do I snipping tool, okay? Yeah, so I just want to open this. I just want to be able to draw. Okay, ignore whatever is. So anyway, so given a line, so let's say you see, let's say this second line, okay? Let's say this one. This what? Let's say this line, okay? So you are hitting here, so there is a tangent line. You see, that is a tangent line. Okay, so this A, B. So let's say this A, B, C, okay, the ray B, okay. So it hits there, and how does it reflect? Well, the way you find that out is you draw a line perpendicular to this tangent. So that's a normal, okay. So this is a normal. This is called normal line, okay. Then you just by symmetry, you can see the reflection line is this one. Okay, reflection, Flection. Okay, this is the reflection. You see, by symmetry, because you just find the angle. So you find the angle between the line, this ray and the tangent, then you just reflect it over this axis, and you get that. Okay, so that's kind of the math background. So in order to answer this question, you can work it out by slowly by trying to find how do you specify this vector first in the first place. So you can imagine it's the move the whole graphics to the origin. Like you can imagine if it's just a vector like over here. So basically this point is the origin, so it makes everything easier. So because then you can find out reflection, because to move things away from the origin, all you have to do is just add a point. You see, vector addition or vector subtraction, right? So anyway, so this is how you can work it out. You see, this method, thinking clearly, you can not just work it out, you can always remember. It's not like, oh, I need to look up the book about formula, memorize it. No, you think logically. Okay, so you can always derive the formula yourself. I can do it now, but it'll take me like 30 minutes. I did this long ago. So but the point is I can derive it. That's the key when you do mathematics. You don't want to memorize, you memorize derivatives or integrals, by this method. That's not good. You want to know how it works. Okay, once you know how it works, then you can derive it on the fly. So you don't have to memorize it. So it works in every mathematics, like advanced, complex analysis, graph theory, and so on. Okay, shit, we forgot to save a stupid Microsoft. Anyway, so we're gonna code. So let's look at the code. So git directory, search for curve. So you can see my packages. Search for this here. That is a package. And we are looking for caustics. There. That's, you see, we got the code here. So caustic line length, that's one of the options. Specify the length. So actually we need that, you see. So let's copy that. Let's go to, we need that nephroid. So is this what we're doing? Yes. So you need to say here, okay, so actually caustic line length, okay. So you need to say that somewhere. We need that eventually. Then we also, let's go back here. So search for caustic. We caustic origin, already have that. Okay, style, we don't care. So but we want the code, like how do you compute the caustic here? Okay, here is the function. So let me explain to you guys there. That's what we want. Okay, go back to the code. We will explain this code. Okay, now, okay, so this is one thing. Let's put it back, but let me explain the code. Okay, now put it out. So So here is the code that is the heart of drawing all these caustic ray reflections, you see, used in many packages. Let me show you one of them. Beautiful. It's most amazing. So let me show you an example. Go here. So you need to go to deltoid. Deltoid is the curve formed by rolling a circle inside a larger one with a rolling circle 1/3 the radius of the larger one. Okay, then you create this deltoid curve. It can also be created if the rolling circle's radius is 2/3 of the large one. They create exactly the same curve. Fascinating. Deltoid. Okay. Now deltoid. Now let me show you another one called asteroid. It's created if you have a circle 1/4 of the larger one. You roll a circle inside the larger one, but the rolling circle is 1/4 the radius of the larger one. You get asteroid. A curve with 4 cusps. Cusp means these sharp points. Okay. Now, so you got asteroid, you got deltoid, very similar. Okay. But now there's a relationship between these two. Okay, and that relationship is optical property, caustics. Okay, so now let me explain. Fascinating, this one. The most amazing theory. Well, one of, so there are so many amazing relations and properties about these curves, you see. So given an asteroid, you roll a circle inside another 4 times smaller, you create this, given an asteroid, and you shine a light from outside the curve, so from far away, let's say you shine parallel rays, okay? Oh, okay, so wait, given a deltoid, look at the center, okay? So let me show you, look at this one, okay? Given a delta, can we enlarge this? We need to recreate that. Open image, a new tab. Yeah. So given a deltoid, look at the thing in the middle, okay? Then if you have a bunch of light rays, parallel light rays, shines onto the deltoid from outside, and the reflections and refractions will form the asteroid, you see. Does not matter which direction the light ray come from. You see, the light ray can be anywhere. Their reflection on the deltoid is asteroid. Do you guys find this like amazing? So this is super amazing. Okay. Anyone here, say hi. Okay. So so I sent here because I have to watch your videos. I don't think I should be modifying Lisp. Oh, okay. Yeah, super cool. Yeah, so you mentioned screensaver. Yes, screensaver. There's a lot of screensavers based on these curve ideas. So anyway, and we have, so this is a GeoGebra illustration. Actually, let me show you that. Okay, so this is very interesting. So you can see this dynamically. So you see, in the middle, you see this blue, it's a deltoid, okay? Now there's a light source. You see, I'm dragging I think the point I'm dragging is a light source. Yeah. You see, outside of the deltoid, okay? Then you can, and then you look carefully on the reflection. You see, the reflection is this asteroid, okay? Okay, so one part is reflection, the other part is refraction. That's right. I think, yeah. So the reflection and refraction on the deltoid creates the asteroid, okay? Can you guys see? Let me do this slowly, okay? This is just amazing. That's one of the most amazing thing. It's quite amazing. Now, how do you prove this? Actually, I don't know a proof. I asked a mathematician one time, but he didn't know neither. But so I did this like 30 years ago. I should actually try to find a proof and see how to prove it. It's not. Is it easy? I'm not sure it's easy. It involves, I think, the concept of envelope anyway, which is, I think, involves differential equations. I'm not sure how to prove. Okay, so actually, let's try AI. So this is a very difficult question. Show proof that caustics of parallel rays on deltoid is an asteroid. Let's see AI can answer that. This is like very difficult. I mean, this is not, I don't think it's a common question. Show proof that caustics of parallel rays on deltoid is an asteroid. Let's see what Grok will say. So this is digression. Yeah, so let's see. You see, how powerful are you, AI? Can you prove this? I would be very interested because I've never seen proof myself. Okay, deltoid uses equations like thinking about user's request, thinking standard deltoid, assuming rays parallel to x-axis. Okay, features 3 cusps and concave inward curves. That's right. Recalling evolute relation where deltoid evolute ties to asteroid caustic. What does it? Now searching the web, you see that American Mathematical Society, that website contains my page. Well, due to this mathematician John Bayes. You see this blog.ams.org. John Bayes, about 7 years ago, like posted my page about this deltoid and asteroid. So to the American Mathematical Society. Anyway, so it's still thinking. Okay, you see, this is not an easy question. I've never seen a proof, and I don't know how difficult does it involve. So, okay. Fascinating. Hi, Coffee. Hello, been a while since I've joined in a stream. Hello, Coffee. For the past month, I've been coding a lot Wolfram language. Dabania. Fascinating. AI usually answers me before I ask. Yes. Okay, so AI is actually still thinking, so I don't think it'll come up with a correct answer because it's like trying to do its stuff. I don't think it's gonna come out a correct answer, but the answer, whatever answer it gave, is probably helpful to find the proof. You see, it's still going. You see, that is why I learned about these many properties of plane curves. I started to write programs, when I was 20 years old, so that we can visually prove it. I mean, visual proof doesn't count, but at least we can like visually see that is that's kind of true. This amazing property, like you can visually see it's true. Now, before computers, mathematicians do geometry. It's very like strictly logic. There's no like for a period of time, they don't do illustrations at all. because they try to stick with pure logical analysis, right? So when you say, when you given this theorem, asteroid is the caustic of deltoid with parallel rays in any direction. Like people, when you read that, like you don't know what's going, like it's very dry. But in your head, then you might imagine like this picture, but it's like very fuzzy, like it's hard to imagine, right? Like asteroid is the caustic of deltoid with parallel rays in any direction. But with computer technology, you can see it. And of course, the interactive technology, you can actually see close, in detail. But still, you need a proof. You see, AI is still going. Fascinating. I've never seen a proof. So, I want to show you this deltoid and asteroid. Okay, I want to show the American Mathematical Society. That's a professional organization for mathematicians. So if we go there, this is 2013, about 10 years ago. You see, this is by Professor John Bayes. He taught me a lot mathematics. We don't know each other, but we know kind of online, so online, he wrote a lot about mathematics. So I learned quite a few math from him. He's one of the top mathematicians. So anyway, so he wrote this, and he borrowed from my website. So I'm very thankful for for having my website shown on the professional mathematicians blog. So anyway, but then I asked him that, do you know a proof, by the way? And he says no. So I wanted to see a proof, okay? So, but I have not seen. I don't know how to do it though. So you see, AI Guac is still like thinking. I've never seen Guac took so long. This by now is like 2-3 minutes. Interesting. AI is much interesting. They do courses on it in college nowadays. Really, yeah, there's so much, we don't know what's gonna happen. Anyway, so let's go back to the code, okay? So how long have I been talking? Already 70 minutes, okay? So anyway, this is the code that does the reflection and refraction draws, okay? So how can I, like, what do I want to do? So first of all, let me do a quick demo using this code, okay, to show that what it does, okay? Let me just quickly, so let me show, okay? So for this part, let's go to talk show, okay? So wait, let's go to today's talk show. Okay, then go down, new section. That's the question we asked AI, and I wanted to show this this AMS American Mathematical Society link. Okay, and we wanted to, I want to demonstrate this code, how it works. Okay, so this code, caustic lines, takes a bunch of points. Let me change that, rename it. Okay, so okay, it takes a bunch of points and tangent vector points and ray origin and the line length. Okay, that's line length. Let's just say length. Okay. Wait, it should do. Okay. Anyway, so that's the argument, it returns a list of lines. They represent rays from ray origin shooting towards the points on the parameter curve and reflected. Okay, each line length is x length, including the reflected portion. Okay, so how do you do this? How do you what's the example of using this code? Let's do it. Okay, so let's yeah, so let's call that function, and the function takes this bunch of things. Okay, points, let's say cosine sine, cosine sine x. Okay, then you want to map them x from 0 to, let's say from pi to, let's say from 3 to 6. Okay, it's 3 to 6 in increment of 0.2. Okay, now that's the points. Okay, now you want the tangent vector. Well, tangent vector, that's a list of tangent. So how do you, what is the derivative of cosine and sine? I believe derivative of cosine is negative sine. Derivative of sine is negative cosine. Is that right? I forgot. So, but let's try to find out. Yeah, so that and the derivative. Okay, let's see what we get. Fantastic! I was correct. 30 years of derivative I never thought of. I was correct on that. So that's a derivative. So what you want is this function. Okay, so okay, then well, let's just copy it. You just say table that from 0, 3 to 6 in increment of that. Okay. Okay, so you delete that. So that's that is the tangent vectors. Okay, those are tangent vector points. Then ray origin, let's say what was the origin we were using? I forgot, but oh yeah, so 9 and 20. Okay, so ray origin 9 and 20. Okay, and length, let's say 99. Okay, so that is the actually, so that is the input to that, to this. Okay, so I actually copy it. It returns a bunch of lines, so you need to output to graphics. Okay, okay, so cut that. Okay, copy all, and I think that's it. So paste the code here, shift enter. Wrong, we got something wrong. Okay, well, we can fix it. Let's see what is the coordinate, something oh, we need some other code. What? Oh yeah, we need another code. We didn't copy that thing. Okay, reflect director, reflect direction vector. Okay, we need to get that. That is simple. Okay, so go to Git there, search for that there. Okay, so actually we need this function. That's why, you know, all these dependencies we don't want. That's why I'm removing all these dependencies. So this is actually, so this is how do you get the reflection and refraction. Okay, involves dot product. Pretty simple actually when you actually once think about it. Okay, pretty simple. So anyway, copy that. So go back to our code. So you just go there and Okay, so now copy all, paste it, shift enter. Fantastic. Now you got something wrong. Why is it okay, you don't want the line length, let's say line length 29. Okay, so you see, fantastic and beautiful. You see, now you see, it actually works. So you just need range, plot range, okay. Fantastic and beautiful. Plot range, you need -1 to 1. Okay, that's x and y and multiply by 20. Okay, that's how we do. And copy all. And let's just open a new one, paste, shift, enter. Fantastic. Okay, so you don't want 20, plot range 20, plot range. Let's just say 2, shift, enter. Fantastic and beautiful. Can you see? So this is like how the code works. You know, okay, so, well, I think that's it for today. You know, I should actually explain exactly how this reflection works. But, you know, let's magnify, but, you know, then we need to, what I need to do is actually, so, you know, I should explain how this works. So reflect director takes 2 arguments, ray vector and a wall vector. Okay, returns a unit vector that is the ray vector reflected off a wall vector. Okay, the ray and wall vectors do not have to be unit vectors, and if the wall is the 0 vector, then 0 vector is returned. Okay, that is a function. Now, what does it actually do? Well, if it's when the wall vector is 0, then just return 0. 0 vector is, you know, it's like divide by 0. You don't want that. So otherwise, here's a formula. So you just negative ray vector plus 2 times. Okay, that's a dot product times wall. You know, I don't I don't remember the details, but okay, here's what we can do. Okay, so let me show you. So you can actually find the formula. So let's say A, B, because Wolfram Language does symbolic computation. X, Y. Okay, so let's see. Given a ray vector AB symbolic and given a ray wall vector XY, what is the reflection? Do it. That is the answer. Okay, so yeah, so you know, so actually just the normalized part, because the other part is testing if xy is 0 vector, you know. So let's just do this part. What does it? Okay, so that in terms of A and B, that's the formula. Fantastic. Let me demonstrate the Wolfram automatic formatting again. You see, automatic formatting on the fly of programming code, not just simple programming code, but mathematically typeset code. You see, they can format it on the fly, unlike the Python idiots, the JavaScript idiots, the C++, you know, the industrial coding idiots. Okay, let me demonstrate that again. In Notebook, Wolfram Notebook, you can format this on the fly. You see, as you type. Okay, and not just simple code like this. You know, for example, can we yeah, you know, not just like simple code, which it does format on the fly. You see all this indentation. There's no tab there. It's like just rendered on the fly. You see, indentation. You see, they do it in a intelligent way. You see, indentation and line wrap. You see, and it can do that for code, and you can actually double click it. It will expand selection according to the syntactical unit of the programming language, Wolfram language. You see, double click on that, double click, you see it selects this entire list. If you click, you do again, it select entire if statement. You see, then if you expand, it select entire map thread. You see, or if you start from that map thread, you click twice, it select the entire map thread. Semantic unit, syntactical unit. You see, so this Wolfram notebook, the front end, it understands the Wolfram language syntax. You see, so for example, let's select any, for example here, double click again. You see, it automatically goes to the plus normalize. You see it select the normalize and whatever part together, because now this sum that plus that is one unit. You see, now if you click again, it's gonna select this line unit. You see, let me show. Okay, double click, triple click. You see, let me do it again. Click. Okay, click. You see, let me try again. Okay, click. You see, it expand the selection by the syntactical unit and semantic unit. They actually are in sync. Why are they in sync? That is because of the Wolfram language. Every syntactical unit corresponds to a semantic unit, just like Lisp. Okay, that's not the case for C or C++ or Java or JavaScript, these idiots, or Python syntax. Like in those languages, there is no systematic correspondence between syntax and semantics of the programming language. But in Lisp language, it does, because in Lisp, everything, the parenthesis serves as the unifying force between the syntax and semantics. So it corresponds well. Every syntactical unit is also a semantic unit of the programming language. Okay. Now in Wolfram language, that's also the case, because Wolfram language actually, I've explained before, it's actually based on nested syntax. Okay. So anyway, all this you see all this plus sign or equal sign or double equal or the nest, the curly bracket, those are just syntactical shortcuts. Okay, or the greater than, let's magnify. Let's see the full glory. You see the greater than equal sign, there, or the pi sign, or the ampersand. Those are just syntactical shortcuts. They correspond, actually, they have a full bracket form. Anyway, I'm digressing all over. So right now I'm just mentioning on the side this great concept of the editor understand the several things I mentioned. The feature of expanding selection based on syntactical unit. That's one great idea, great feature. Okay, and the concept of a programming language where the semantic unit and syntactic unit corresponds, which applies in the Lisp language and Wolfram, because Wolfram is actually, you can think of it as a Lisp, okay, because it has all the properties of Lisp, meaning symbolic, everything is symbols, predominantly functional programming, and purely nested syntax, which I can show you, but not here. This is a shortcut. Purely so symbolic, predominantly functional programming, purely nested syntax, list macros. In the case of Wolfram language, it's actually more full-featured, called term rewriting system. So it satisfies everything about Lisp language, the special properties, and every symbol in Lisp, for example, you have several slots like value slot, you have properties and stuff. So same thing with Wolfram language. Okay, so Wolfram language is very much like a Lisp. So I mentioned several things. The feature of the editor expanding selection by syntactical unit, that's one thing. The concept of programming language of semantic unit and syntactical unit in coherence is another concept. Okay, then I also mentioned the automatic on-the-fly formatting of Wolfram language. You see, that's another feature. Okay, so we don't see this in like the industrial idiots with their Python or Golang, C++, or even Rust. Like nowhere in their in industrial Google. Oh Jesus, Google AI. They don't have this. Right? Like their brain is dead. This the Java. What's so TypeScript. Type. Open, not TypeScript. Well, TypeScript too, but VS Code. Okay, like you don't see this in VS Code. Nowhere to be found. The idea is foreign. Like they don't understand the thing. They never thought of these industrial coders. Okay, let me mention again. I mentioned this many times. These industrial coding idiots. In their life, they've never seen a scientific programming language. Well, today they started to see some of them because due to AI, because in able to code AI, there's a lot of science involved. Starting like 10 years ago, you start to have data science, statisticians, and you started to have quite a lot of math, especially AI, linear algebra. You need to understand math, but not the tip. Still, most other programmers, like the operating system phonetics, like they talk about Linux kernel, Linux, this, or the web dev. Like most of them, they never seen. They don't know what the fuck is sine cosine. Okay, that's the situation. Okay, we digressed. But okay, but anyway, that's it for that talk. So how long? So are you guys like enjoying the show? Am I like? I'm sometimes I'm pretty sure I get some haters. Python lost its charm for me, so tough to get run dependency. Rust will collapse like Haskell. I think I don't know much about Rust. What I know is that there's a lot of fad. But also Rust is like has a lot of like functional programming ideas. It's partly based on OCaml, the meta language. So so my feelings about Rust is mixed, but I don't think it'll collapse like Haskell, because Haskell is like too pure. Haskell is from academia. Although since 10 years ago, Facebook or some other, there are some commercial organizations use Haskell, but not much. So there was like huge movement, but it never stayed Haskell in a coding industry, because Haskell is like they want pure functional programming. Meanwhile, OCaml, F#, the meta language lineage, is very practical. So I have this pad for my seat. OCaml, so F# is actually used in industry, and OCaml in financial industry. And And Rust is kind of the new thing. So lots of functional programming ideas. It's based on OCaml. So what I don't like is the fad. There's a lot of fad. But however, I think it's actually here to stay, because on the other hand, what we don't want is the C and C++ fuckheads. Okay, doesn't matter how much I dislike Rust, because there's fads. There's a lot of young people fads, but there's nothing compared to the perpetual, the steel forceful C and C++ fuckheads. They should die. We need, in other words, what I'm saying, not the people, okay? What I'm saying is that the industry, we need to get rid of C and C++ and their practice, their ideas, like almost everything about C and C++. That's what I'm saying. So for me, Rust is, I don't know much about it, but at least I think it's better than C++ for sure. Okay, C++ should die. Golang is not a bust. In fact, so I guess you are new. Golang is, I believe Golang is one of the best language. Okay. Hi, Xah. Why? What do you mean why? Okay, so I think that's it for today. I already talked for 90 minutes. Is that right? Yeah, 90 minutes. Would you characterize the syntax of Wolfram language as more like Lisp or Prolog? It's Lisp. Okay, so I talked about this many times. In fact, in the past 30 minutes. So there's a lot of videos I've done talking about Wolfram language compared to Lisp. So let me show you a few, and that's it for today. Okay, so Xah Lee, Wolfram, Lisp. Just search that and see what you find. Wolfram language tutorial, no. Wolfram language versus Lisp syntax. Okay, that's one of my article. Okay, and you should read that article. So this is Wolfram language versus Lisp article 2013. Okay. No, this is not the article you should read. The 2013 is kind of early, okay? But you can read it, but I have much better articles since. So you should read actually all these, okay? If you guys are interested in what I just talked about in the past 30 minutes about these language issues, you should read like all of these, okay? Many of these. Fundamental problems of Lisp, syntax irregularity, Lisp infix syntax survey, nested syntax XML versus Lisp. Actually, that's not a very good article. That's kind of half-assed. I need to write more about that. Concept and confusions of Lisp prefix, infix, postfix, and Lisp. Okay. Let me open a few of the articles that I recommend you guys should read if you are interested of what I talked about in the past 30 minutes about these syntax and issues. Okay, so let me open them, and so people don't waste time. Okay, so yeah, that okay. And also, I haven't answered your question yet. The difference of Lisp and Wolfram language. Wolfram language is not based on Prolog at all. It's Lisp and APL, and I have an article on that. Okay, actually, just search for Wolfram language, Lisp, and APL, and maybe put my name. You'll find my article, because I show the historical documents and why it's like that. Okay. So, but meanwhile, and also I've done videos, so I haven't, so I, so go back here. So you click on the videos. So let's say go to videos, Xah Wolfram Lisp, go to video section. Okay. So I can tell you, episode 7, so I've done, I've done hundreds of videos, about 5, like I would say 5 or more, full 1 hour talking about the Lisp and Wolfram language relations, okay? But it's hard to search like this. Yeah, so it's not, it's hard to search like that. So you need to, okay, so let me show you what guys to do, okay? Xah Lee Emacs, go to my Emacs section, Xah Emacs tutorial, okay? And go to Emacs blog, and there is a Xah Talk Show video live stream. Xah Talk Show 2024, June 11th, episode 558, which is best Lisp, common Lisp scheme, Emacs Lisp closure, Wolfram language, okay? That's one of them you could watch, but yeah, that's one of them. Watch that, okay? But so this article is also good. Fundamental problems of Lisp, syntax irregularity. Yes. Then okay, so that one, and this one is also very good. Lisp infix syntax survey, because lots of Lisp coders, they don't want, I mean, they are trying to create a non-nested syntax, okay? So there's lots of effort throughout the years by top Lisp experts, okay? These are top Lispers. They created them. They want them, including the creator of Lisp, John McCarthy. They didn't want the purely nested, thing. They want something else. Okay, so that's the article, one of them. And this one also important: concept and confusions of prefix, infix, postfix, and Lisp notations. Okay, important article. So read that one too. And I'm not sure about this one, but I have better ones to show you. So okay, so let me just show you. Okay, then. So you go to Xah Wolfram. Yeah, let's search. Let's not use, because when I search, people can see, they can replicate. Okay, Xah Wolfram language. Okay, you just go to my Wolfram language website. Okay, there. Then once you are here, you go down. There's a section, Wolfram language history. Okay, so you wanna read Wolfram language design, Lisp APL history. Okay, read that one, and this one. So let me show you. So this one, Wolfram language design, Lisp APL history. So I show you historical documents why Wolfram language is a combination of Lisp and APL, and Stephen Wolfram's own idea about a term rewriting system. Okay, that's the essence of Wolfram language. It's the pure essence. Lisp, from the Lisp heritage, like the syntax is like everything Lisp, and from the APL heritage, where basically it just means everything is an array. It's an array language. Like what that means basically is that every function, when it applies to an argument that is a nested list or matrix, it automatically applies to each element. Okay, that's the kind of APL. Okay, it's called array languages. Okay, now you combine these two ideas, everything Lisp, but instead of using the paren, you use the symbol and square bracket. Okay, then comma instead of space. Okay, so combine these two ideas, then combine the idea of a term rewriting system. You can kind of think of it as like Lisp macros, okay, but complete. In computer science, it's called term rewriting system. To do mathematics, that is Wolfram language. It was called Mathematica for the first 20, 30 years. Okay, it was named, the language is now given a name, Wolfram language, since about 2015 or so. Okay, so it was called Mathematica. Okay, that's the idea of, that's the essence of Wolfram language. Now let me show you. So this is like my Wolfram language code from 1990s, 30 years ago. Okay, and so now so let me show you the go back. So this article, okay, so Wolfram language versus Lisp. So in this page, I give you a comparison of everything that exists in Lisp, such as Common Lisp scheme, Emacs Lisp, and the corresponding thing in Wolfram language, okay, side by side. This is like 10 pages. Okay, so first of all, you got symbols. Identifiers are symbols. Check. Everything is an expression. Check. An expression is either a atomic expression, such as number, string, symbol, or a list. Check. Purely nested syntax. Check. Predominantly functional programming. Check. Lisp and Wolfram, both. They are like that. You can have variables, you can change variable values, but predominantly it's functional programming. Okay. Reader macros, meta expression in Lisp, check. In Wolfram language, that's called syntactical shortcuts. Okay, that's why you are seeing, like if you came from Lisp, you are wondering, no, this doesn't look like Lisp. You got equal sign, you got square, curly braces, you got comma, you got double equal sign, you got pound sign. You might think, oh, that doesn't look like Lisp. No, you are wrong, because in Lisp you also got this Markov characters, such as the pound sign, stand for function, and several others, such as comma. So anyway, so these are called in Wolfram language, they are called syntax shortcuts. Okay, actually they don't call it that. They just call it the normal standard form. Okay, like most people would be freaked out if you call them like lambda or like computer science jargons. Wolfram doesn't like that. Okay, in Wolfram language, it's just normal. Okay, I mean, they don't have like this is called, by the way, sex. That is called meta expression. Or this is called lambda. Wolfram language does not use the in-end or whatever the abstruse jargons. Okay, they use whatever terminology that's most easy to understand. So, for example, they don't call their function lambda. It's just function. Okay, not lambda. They don't call it sex, symbolic expression. No, it's just full form. Okay, so on the left side, these are called full form. On the right hand side, they don't have a name. It's just syntax. Okay, they don't have a special name. Okay, but they are equivalent, because every time the Wolfram compiler or interpreter runs code, first thing it does is convert the right hand side to this this short syntax to the fully nested form. So in Wolfram language, in fact, everything is this fully nested. Like most people don't know. Anyway, so I was talking about. So if you go back, so check. So then Lisp macros. So Lisp got macros. Wolfram's got the full-featured pattern matching. So in other words, in Wolfram language, in fact, the entire program is computes by pattern matching. Okay, all this you see are in fact actually well, not here, but most, like half of the code in Wolfram language is pattern matching. In other words, think of Lisp, where most of your code is written in a Lisp macro style. Okay, that is Wolfram language. Full pattern matching, not just like Lisp macros, like idiots. Lisp are really like idiots. I really despise the common, especially the common Lispers. They are like idiots. But the reason they are not the original Lispers, like the John McCarthy, which I respect. But today's Lisper, the common Lisp phonetics, they are like idiots, okay? They don't know about functional programming. They think, oh, you need object, like Lisp object system. Oh, that's so good. You fucking fuck the common Lispers, okay? They don't know what they fucked up every good idea of John McCarthy, the creator of Lisp. Okay, that's what I'm saying. Okay, so you got this. So you got to read that. So watch that. And so did I finish that? I think that's it. Okay, so this article, every comparison about Lisp and Wolfram language is here, and then I show you actual every detail, like the syntax on the left hand side. On the left, you see Lisp nested paren. On the right, you see the bracket, the nested bracket. Comments, then expression grouping. In Lisp, you have prog n. In Wolfram language, it's called compound expression, more logical name, okay? Not prog n, like what the fuck is prog n? Compound expression, logical name. That applies to every Wolfram language name. Or the short syntax is just semicolon. You see this semicolon here? You see that semicolon? That's actually short syntax for compound expression, you see. This is like advanced, you wouldn't know until you dive deep into Wolfram language. You see that semicolon? That actually is equivalent. You can rewrite this by changing that, this line into the compound expression, okay? And then square bracket, then this line, okay? Then you don't need the semicolon at the end. So for example, this part and then this part, they are like part of the compound expression. So instead of semicolon, you use a comma to separate that and that. Okay, so that's do I make sense? Like okay, so let me show you again this for those you haven't seen it. We did this today. Fantastic reflection of light rays, and this on the fly code formatting. Okay, not just programming code, but typeset mathematics and on the fly formatting of typeset mathematics. Okay, these technologies began in Wolfram language in 1996. Wolfram language Mathematica version 3, okay? And to this day, in the industrial coders, the C++ idiots and LaTeX, these idiots, they don't have this, okay? They actually never seen it in their life. The Python idiots, okay? So anyway, and the common Lisp fuckheads, because I've been trying to tell the common Lispers this about 30 years ago. Every time I do, they will attack me. They will say, no, you are just a troll. You don't know nothing. You see, I started my life coding Wolfram language. Then I got very interested. Why am I into Lisp? Because, I'm into computer AI, that's, so they are all related. In fact, it so happens that Wolfram is actually part of Lisp. So I started to learn Lisp, and I got, questions about why is Lisp, why do you have cons? Why, how come you are not consistent? How come you, so I talked to the Lispers. Then, well, part of it is because I'm not a, like nice and polite, like social kind of person. So they call me a troll. They don't. But part of it is that they just don't know. They don't know. They don't understand. They are like the industrial coders, the C and C++. They don't know the essence, the why is John McCarthy Lisp, the creator Lisp, created a evolution. They don't know, these people. So they anyway. So that I think okay. That's it. Coffee says, I still got Wolfram 9 on my old computer. Wow, amazing. Wolfram 9. Now, what year is that? Wolfram 9, is that 2008 or something? I know plenty of Common Lisp hackers who don't like clause. That's okay, that's good to know. I fucking despise that Common Lisp object system clause. Because like every time you talk to the Common Lispers, 2012, okay. Like every time you talk to the Common Lispers, like a lot of them will mention this Common Lisp object system. Fucking idiots. Fuck them. Lisp is not supposed to be object oriented. But this Common Lisp phonetics, like they don't know. They think object is good thing. Fuck them. So I very despise, I don't get along with a lot of these, these Lispers. I can understand part of it is just because my personality, okay? But part of it, they are like idiots. Okay, bye guys. That's it. Also, did you see Olin Siever's work on array polymorphism? No, I know that guy. What's up? Did he do like he's he created scheme shell? Olin Siever's he created scheme shell. But I don't hear any news from him like in the past 10 or 20 years. Is he still teaching at, he must be very old by now. Thank you for the stream. Thank you guys. Bye guys. Bye guys.